Hello. Hello. Check. Hello. Mic check. Hello. Hello. Check. Do you want pointer or we'll do manually?
Is there a thing?
Yeah, but you have to insert your additional gadget for the receiver.
Let me not fiddle. It's fine.
Yeah. So you can
That's
use
there.
pointer. Yeah. You can use pointer.
Okay.
But you can change it to it.
Yeah.
Just say something.
My test 1, 2, 3.
So you can adjust your video in the view also. You can find whether you are comfortable with it.
What video?
This video. Just yellow frame.
Yes.
If you are out of the video, you can just.
Oh, I see. So, so this is my video.
Yeah, this
I
is
see.
Right.
I see. So that
Yeah,
is from this camera?
No, this camera.
Oh, it's from this camera. All right.
So the camera edge screen will follow your screen whenever you're going to, and this one will be closer on that.
Okay. It's just getting complicated.
So I have to take the.
Sorry. I have to do what? I hope, yeah, that's not so.
Hello. Okay, so it's actually 2 minutes past 4 o'clock, and I would like to welcome all the audience joining through the YouTube channel of TIFR, the Platinum Jubilee channel, as well as those who have joined us through the Zoom, and of course, the people in the auditorium. I welcome all of you for this edition of the Wednesday Colloquium. And this particular colloquium is special because we have a speaker from within TIFR, Professor Basudeb Dasgupta, who is going to give the colloquium today. Before I actually move to Basudeb and give a few words of introduction to him, I would like to mention that this colloquium, of course, is the original brainchild of Professor Homi Bhabha, our first founding director. And it has actually carried on pretty well. It has aged pretty well for almost 70 years in the institute, as this has brought together physicists, chemists, and biologists at least for one day or one session under one lecture theater, and actually listening to experts, relevant experts in one of the scientific communities talk about the work for a broader audience. And this has actually enabled faculty members within the disciplines, above disciplines, as well as students to interact with each other and discuss that talk. So that's a big benefit and training for the students, as well as a fantastic playing ground for faculty within the institute for collaborations. So today we have Professor Basudeb Dasgupta, who is one of the young, bright, rising stars in the TIFR community. Basudeb actually started in almost 6 years back in the institute, and he has risen to ranks. But one of the most amazing things about Basudeb is due to his wonderful work, in theoretical physics, he was recently recognized by the international community. He won the ICTP prize almost 2 years back. Something that is a matter of pride, as an international community recognizes the work that comes from a person from India, as well as he actually now is included in the top 75 people shaping country under the age of 50 years. So DST released a list, of a few people in the country who are sort of very important in shaping the academic future of the country. So Basudeb was recognized as one of these top 75 people doing that. So without further ado, Basudeb, I would like you to.
Thanks, Jyotishman, for perhaps that unkind introduction. No, I appreciate it. It's wonderful to speak within my own home. I did not join TIFR 6 years ago. I've been here for like an extended period before that, and anyways. Okay, this is a joke. I appreciate your warm words of welcome. Okay, so I'm going to tell you about some work that we've been doing over the last 6 years. This is the work of 2 graduate students, and I'll mention them as we go along. So yeah, let's jump right in. So I don't think the exponential function needs an introduction to any audience for that matter after the last 2.5 years. Okay, everyone knows the exponential. We know exponentials are horrible. Exponentials are terrible, and exponentials create difficulties for some reason, and we also know that they arise for some very special reasons. Not everything rises exponentially, but they're very ubiquitous. So what I show here in this slide, yeah, the population rises exponentially. This is Moore's law, the number of transistors on a chip rises exponentially with time. This is the spread of a fire rises exponentially. This is the number of counts from a nuclear chain reaction rises exponentially. So all of these have something in common, that they start exponentially. And you might ask, why is it exponential? And it has actually a very simple answer. Anytime something grows at a rate that's proportional to its current state, you get an exponential. That should already tell you that phenomena that involve interactions with itself in some way. Okay? So 2 people have to meet to create children. 2 people have to meet for a virus to infect the other. No, the neutron produced from one nuclear reaction needs to do something else somewhere to produce the next reaction. All of these examples have something in common, that the previous step influences the next step in a way that leads to faster and faster growth. The slope increases with time. They also have something else in common. This does not go on forever, thankfully. Okay, should be grateful. And the reason why it doesn't go on forever is something runs out. There is a natural cutoff. There is something that leads to a saturation effect. In a nuclear reaction, maybe the fuel runs out. In the case of populations, perhaps the system becomes incapable of supporting more than some number of individuals. There's not enough food left. In the case of transistors, we may be getting close perhaps to the limit that physics allows because of, so you have to make these chips, you have to, basically pattern something on a semiconductor. You do that using light. And you can't get any smaller because the wavelength of light, is a resolution limit. That's your ceiling for the Moore's law, at least for now. So there are natural cutoffs. What you'll find very interesting, and if you've been following epidemiology modeling for COVID for the last 2.5 years, modeling this early rise is easy. Practically anyone in the first 2 weeks of COVID in March 2020 could have taken the last 10 days of data, put it on a log plot and drawn a straight line through it. I did it on Facebook, many people did it. It's straightforward. nobody predicted when the peak would appear. Okay, nobody. There's been a lot of controversy. I don't think anyone can honestly claim that they predicted the peak, reliably. That tells you that this is a hard problem. So predicting the exponential rise is not very hard. This is much harder. Just for setting the tone. So this is the exponential function where both the independent variable, in this case time, and the dependent variable are drawn on a linear scale, where equal divisions are equal increments. Sometimes I will use a log scale on the y-axis. On the vertical axis, I will use a log scale. Here, equal divisions correspond to equal ratios. Okay, so this is a factor of 5. This is another factor of 5. 5 divisions between 0.01 and 0.5. So equal, that's the log scale. On a log scale, the exponential looks linear. Okay, so that's the only thing that you need to remember. Sometimes, basically, when you see the vertical axis as having labels like 10 power minus 1, minus 3, minus 5, minus 7, equally spaced, that means there are equal ratios of 100. And in that scale, if you see something is approximately linear, that means you're looking at an exponential function. Okay, as long as the x-axis is linear as well, which it will always be. Okay, and then saturation looks like this, which is fine. So what is this talk going to be about? It's not about COVID. This talk is going to be about neutrino oscillations. I'll tell you what they are. Inside supernovae, I'll tell you what they are. And the fact that sometimes these neutrino oscillations grow exponentially. This is not the usual case. Something crazy needs to happen for this exponential growth of change of neutrino flavor. So that's what this talk is about, and it doesn't always happen. It happens sometimes. So this blue curve, you can see, this is my vertical axis in the log scale, minus 7, minus 5, minus 3, minus 1. And you see this part is approximately linearly rising. That's the exponential rise. Basically, it rises by 4 orders of magnitude in a very short time. So that's what we call an exponential here. And then it saturates. But you might say, well, it doesn't grow very large. It's just saturating at something like 0.1. But what's being plotted only goes all the way to 1. So once you reach order 10%, basically, that's all you can do. After that, something runs out. Some resource runs out. In this case, that's unitarity. Probability runs out. So we'll talk about that later. So this talk is about why does this blue curve even exist? And when do you get this red curve where things don't increase exponentially versus when do you get this exponential increase? That's question number 1. Question number 2 is that, okay, if this exponential increase in flavor change does occur, why should I care? Okay, so whatever, something is happening inside some star, neutrinos are oscillating, why should I care? So I'll answer these 2 questions for you. Okay, why do neutrino oscillations increase exponentially under certain circumstances? That's question number 1. Question number 2, if it happens, what does it do? Okay. And so this is the summary of my talk. I like to start with the summary so that people who want to turn off and turn on their phones after this are welcome to do so. This is the summary of the talk. Usually, neutrino oscillations are described by a Schrödinger-like equation. So this is the time derivative of the wave function that depends on the Hamiltonian acting on the wave function. And this wave function is a multi-component wave function, let's say 2-component wave function. And you go from one component to another. This is called neutrino oscillation. It happens at some rate that's approximately once per kilometer for the numbers, for the values of the neutrino masses and energies that we are familiar with. Once per kilometer. In a supernova, something else happens. This equation becomes more complicated, and I'll tell you why. because neutrinos are very dense inside a supernova and they start influencing each other. And as a result, this rate becomes much faster. It becomes once per millimeter. Okay, it's approximately 1,000,000 times faster.
Can you just
Yeah.
Just for the sake of people who are outside the field, how does that? Can you give a feel for the rate? What does the delta m square by 2e really mean?
I'll tell you. So this is the summary. It's for experts.
Okay, sure.
I'll define every single symbol on it, within 2 minutes. Okay, so there's a rate at which this flavor conversion happens, which is once per kilometer normally. It becomes once per millimeter, 1,000,000 times faster inside the supernova. I will answer for you when is this possible, and the answer is that when the momentum distributions of the two flavors cross each other. So you draw two functions, and if they intersect, then this is possible. So I'll prove this for you mathematically. And the second thing is that what impact does it have? And that's a saturation result. Now I'll prove to you that at the end, it leads to some kind of equilibration of the two flavors, but not perfect equilibration. An equilibration that is momentum dependent. And then once you have that, that leads to or can lead to changes in how the star heats up because of neutrinos and how elements are created inside the star because of neutrinos. Okay, so that's the last part. So am I clear so far? Any questions?
So just a clarification here. The curve you showed earlier talked about what fraction is undergoing this change, right? So are you talking about that the rate is different for different subsets of neutrinos, or is the rate changing for all the neutrinos?
Yeah, so we'll come to that, but the quick answer is that what I say is what fraction of neutrinos have converted is equivalent to the probability that any one neutrino will convert. So this is the conversion probability for everyone, for every single one of them.
But the equation is the same for all of them, right?
Yes, yes, yes. All right. So before we start, the most important people. So much of the work done in this talk I'll be showing is from the PhD thesis of Shomo Bhattacharya, who's a PhD student who just left and he's going to write his thesis and submit very soon. Some of the work is from Manibrata Sen, who graduated a couple of years ago. I will not have the time to show some of the wonderful work done by Bhavesh on neutrino detection. We've done some of this work together with Professor Vivek Datar, who is in the audience, and Amol, who might be online. Okay, so I'll not be able to talk about this work. And I have a second life working on dark matter and primordial black holes and what have you. I've talked about those things in previous Wednesday colloquia. Unfortunately, I can't talk about some of the exciting work done by Anupam, who's also going to submit his thesis very soon. So I apologize to them that I can't talk about their work. Today, I must confine myself to work about the work of these gentlemen. I must thank two extremely important individuals in all of this exercise, and that's Kapil and Ajay. All the work that I'm going to show, it might look simple. Some of the things I'll make more simple than they actually are, required heavy-duty computing before we got to solving the equations. Now, we looked at the numerical solution and guessed the analytical answer. The numerical solution requires hundreds of hours of computing on hundreds and thousands of CPUs. This would not have been possible without the help of these gentlemen and without these funding agencies. So the Department of Theoretical Physics kindly provides extraordinary computing facilities. Our chair is here. He should feel proud. All right, let's start. Good, I'm good, doing well with time. All right, so let's start at the beginning. Okay, so now you can ask all the questions. So the beginning is when the neutrino was discovered, when the neutron was first discovered. Okay, so the neutron was discovered, but very soon it was seen that the neutron decays. Okay, the neutron, and it was seen to decay into a proton and an electron. But when this happens, you would expect the electron, let's say the neutron is decaying from rest. Okay, you would expect the electron to basically have the energy which is half the neutron mass. And that should happen every single time. It just can't have any other energy, right? Just energy conservation and momentum conservation, implement that. But what was seen is, if you look at the electron energy distribution, instead of this single energy here, what is seen is some continuous energy spectrum for the electrons. This was a big puzzle. How do you explain that? Okay, so this spectrum is wrong. And this was such a big crisis that it led no less than a person of Niels Bohr's stature to say that we have to give up the energy conservation principle. Okay, so this is the crisis. And out of this crisis comes a desperate remedy. So this is Pauli, Wolfgang Pauli, and he had to go to some party, so he couldn't attend some conference. Instead, he sent this letter. This is actually, the text of his letter. And he says that blah, 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 continuous beta spectrum, I have hit upon a desperate remedy to save the exchange theorem, blah, 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 and law of conservation of energy. The continuous beta spectrum would be understandable by the assumption that in beta decay, a neutron is emitted in addition to the electron. So now what he calls a neutron is actually the neutrino. The name changed later on, but what he's saying is that neutron is not decaying into a proton plus electron, but there's a third thing there, and that steals away some of the energy, and which is why the electron energy spectrum becomes continuous. So that's the invention of the neutrino, not the discovery. Okay, so that's the neutrino invented. And this is no different from the kind of bizarre, exotic ideas particle physicists throw out on the archive every single day. It's just crazy. So you might be wondering, why am I showing you black and white pictures? The world was black and white before the 1930s. So the world was in black and white. So the world became colorful only after the 1930s, right? Right. So anyway, so jokes apart, many years have passed, 90 years have passed. We now know that there are three kinds of neutrinos, nu e, nu mu, nu tau. These are produced in association with the corresponding charged leptons, the electron, the muon, and the tauon. They have masses which is less than a millionth of the mass of an electron, so less than an electron volt. They interact very weakly. So in fact, we know that they interact via weak interactions. That's about, in terms of cross-section, like a million times, let's say, smaller than electromagnetism, if I'm not getting it wrong. And most importantly, and most interestingly, unlike other particles, you have an electron, you have an electron. It's an electron event, after your lifetime, hopefully. With a neutrino, that's not always the case. You have an electron neutrino, it can become a muon neutrino. This is a bizarre quantum mechanical phenomena, which we call neutrino oscillations. And represented a little bit more simply, this is what it looks like. That you have, the probability that your neutrino is in its original state. We call that the survival probability, as a function of, let's say, the neutrino is traveling along some line. And these two curves, the blue and the red, are two different neutrinos or two different energies, E1 and E2, where the blue one is a low energy neutrino, the red one is a high energy neutrino. And this probability is, derived out of some equation that looks like this, which is a Schrodinger equation, I h bar del del t of something is a matrix multiplying the same something. That's the Schrodinger equation. And we want to know the mod square of any one of these components. That's the probability. And that with time oscillates like this. But it oscillates at a rate that's inversely proportional to the energy of the neutrino. So that's the delta m squared by twice e. And what is this delta m square? This delta m square is the difference in the squares of the masses or the squares of the energies of the eigenstate of the system. Okay. So that was a little bit incorrect. Delta m squared by twice e is related to the energy difference between the two states, and delta m square is the difference in the squares of the masses of the two mass eigenstates. Yeah, I think there's a question.
There's a question from TP. TP?
Basu, I think in principle it is possible to explain neutrino oscillations by invoking new physics and yet keeping them massless. So I think this is an assumption. We don't have a proof experimentally that the neutrino has a non-zero mass.
TP, could you repeat the question one more time, slightly louder?
Yeah, I'm saying it is in principle possible to explain neutrino oscillations by invoking some other new physics and yet having the neutrino massless. We don't have an experimental proof that the mass of the neutrino is non-zero. So I think this equation is an assumption.
TP, I understand your question. You're saying that we haven't proved this equation. My answer to that would be that there is no alternative to this equation that is consistent with all available data. We can talk about this more, but I don't want to be drawn into this controversy at the moment.
Yeah, go on.
All right. So neutrinos change their flavor in this particular way, and the amplitude and the rate of the oscillation can be affected by the medium, and I'll tell you why. So this is the amplitude of the oscillation, and the rate you can think of as related to the wavelength of these oscillations. Okay. This is what I meant by once per kilometer, that the wavelength was about a kilometer. Why does the medium affect? Yeah. Yes, in a second. In a second, yes. The theta, this parameter here, decides how deep these oscillations will be. In fact, the depth of the oscillation is sine square theta. It's called the mixing angle.
The drawing is a sine function or cosine function like this?
It's a sine, yeah.
It doesn't look like.
Yeah, it's a poorly, it's my hand drawn sine. Yeah, it has, yeah. So in a medium, this solution changes. Why does it change? Because, Feynman tells us that we can't distinguish between, if we can't distinguish between two processes, we must add amplitudes, right? That's what Feynman tells us. So consider the situation, a neutrino is traveling along this direction, One situation is that it does nothing, it just goes like this. But the another situation is that this neutrino is going, in the middle, it interacts in this particular funny way, and then it again becomes a neutrino, with the same momentum. Nothing has changed. This is called forward scattering. Or take this one, the neutrino going like this, with an electron in the background, it interacts via some Z boson and continues in its own merry way without any change, no change in momentum. This process of a neutrino scattering with an electron in the background without changing its momentum cannot be distinguished from the case that the neutrino did not have the interaction. This is free propagation. So we must add amplitudes. So the total amplitude looks like this. A total mod square is free plus forward scattering square. And this, if you assume, is a bit smaller, which it will be because of weak interactions, gets you a contribution that is linearly proportional to the amplitude of this process. This is called refraction. This is not collision, but this is refraction. Okay, so without change in momentum, if you have forward scattering, you get a phase. And that's what this little calculation shows. And this has to be included in the neutrino oscillation equation. Yes.
In the first diagram, you cannot write the Z possibly.
Yeah, I'm sorry, because you will see why I have written the Z in 1 second.
Yeah.
Now you can.
Sorry?
So now you can, because it can also have a neutrino.
Yeah, now you write the, yeah.
But thank you. Very good. Thank you. So, but you can also do this with neutrinos in the background. Okay, and this gives what is called a matter potential.
Can I ask a quick question?
Yes.
Basudeb, if you go back to the previous slide when you had the oscillation shown,
Mhm.
Can I understand this? The new E and the new mu are the probabilities of survival are being shown there, color coded.
Yeah.
Is that correct? Okay.
No,
And
so yeah, so these are the amplitudes. So this is the amplitude for being a new E. This is the amplitude.
amplitude. Okay.
And then the mod squares are the probabilities.
And somehow you are mixing these two, right?
So yes.
So basically, but you are actually plotting the original amplitude of the individual components.
Yeah, so the two colors are not the two different flavors. The two colors are two different energies.
Energy.
I'm plotting the probability of it being in the original flavor.
In the original.
Whichever you start with.
Got it. Got it. Got it. Okay.
Okay, the survival probability.
Okay. Good.
Okay, any other questions? Yeah.
In the next slide, so
fast diagram new is new E only, right?
In the first diagram, new is new E only if I include this as a E.
Yes, that's
Yes.
for mu it will be.
Yeah, but for the if I'm scattering via neutrinos, I can have anything.
Yes.
Okay. All right. So anyways, the neutrino oscillations has like a 30-40-year-old storied history. It has led to many Nobel Prizes. The key points, however, I want to touch upon are that we've detected neutrinos from the sun and supernovae. And these detections have told us that our models of the sun and of the supernova are roughly correct. And more recently, there has been more detailed verification of this 3 neutrino oscillation paradigm. And there's data from the sun, from the reactors, from accelerators, from neutrinos produced in the atmosphere. And this detailed data is fit through this neutrino oscillation paradigm very clearly. It's just a prediction of, simple quantum mechanics, as I've just showed you. And no other theory does that. This is why we think that this is right. So, but let's leave aside these equations and just develop some visual intuition first. So, neutrino oscillations are, instead of thinking of quantum mechanics, let's do classical mechanics. Okay, simpler physics, hopefully. So, there's this equation: I ddt of something is commutator of that something with the Hamiltonian. That's quantum mechanics. And if I just write these matrices, using 2x2 Pauli matrices, I will get this equation. Okay, that is I just goes away, and you get a spin precession-like equation. That some vector p, 3-component vector p, precesses with time under the action of some vector called b. And the rate of precision is this omega, which is delta m squared by 2c. Okay, so this is, so you have to believe me, or you can work this out for yourself, that this equation is the same as this equation. And so now we can develop some visual intuition. Rho is the density matrix, yes. How am I getting?
Vector equation.
Yeah, so just very quickly, what you do is you take the density matrix and write it as P0 times identity by 2 plus a vector P dot sigma by 2. And similarly, you do this for the Hamiltonian as B0 times identity by 2 plus a vector B dot sigma by 2. Plug this in, commutators of Pauli matrices is epsilon ij k, and you get the cross product at the end. Is that okay? All right. But this is an equation. I believe that for most people, this is a much more familiar equation. This is an equation that you should have seen in school. And this has a nice visual intuition for me. So the neutrino starts out by being along this direction. Any neutrino, let's say the electron neutrino is pointing up like this, and the muon neutrino points down like this. Okay, and the Hamiltonian not being in diagonal in the same basis as flavor corresponds to having a magnetic field which is at an angle theta with respect to this vertical axis. Now my neutrino flavor precesses around the magnetic field like this. Okay, and the projection of this neutrino spin or neutrino polarization vector on the y-axis is the probability that the neutrino is in its own original state or has transformed. So for example, if this neutrino precesses like this and goes here, at this point its survival probability is 1 minus half sine square twice theta. Yes.
There are 3 kinds of neutrinos. 1 to 2.
Yes.
For outsiders who don't know.
Yeah. Okay. Thank you for catching me on my pedagogy. This is only for 2 flavors. If I want to do this with 3 flavors, I'll put Gell-Mann meter. Things are more complicated. But you can think of oscillations between any pair of flavors, even in a 3-flavor story, and that's what I'm describing. And I'll continue to just do 2 flavors for the rest of this talk.
In general, all 3 flavors are always present, or?
Great question. In the context that I'm going to talk about, supernovae, there are 3 flavors, but 2 of them behave identically. So there is a way of writing your equations that you only have to deal with 2, electron and non-electron. So mu and tau look similar. So yeah, so I'm avoiding some details and bookkeeping, but thank you for that question. All right, so this is the picture of neutrino oscillations that I want to use. That instead of all the quantum mechanics, let's just talk about something simple that we understand, which is there's a magnetic field and something goes around the magnetic field. This is clean, okay? So now what happens is that when neutrinos are emitted from a supernova, initially they are trapped in a radius which is about 10 kilometers or so, because the density is so high that neutrinos are just constantly scattering with the nucleons and they can't escape, high optical density, total internal reflection. They slowly diffuse out of this region, which is approximately 10 kilometers in size inside the star. But not all flavors escape at the same time or at the same radius. Why? Because electron neutrinos have more interaction strength with background matter than non-electron neutrinos. So they interact more. Therefore, they have to wait until a bit later where the density has fallen, and then they can escape. So the blue color here is the electron neutrino, the red is the electron antineutrino, and the green are the other flavors. So there are 2 flavors now, electron, non-electron, and then neutrinos and antineutrinos. And they have different interaction strengths, which decides how they decouple. So they decouple. Once they decouple, neutrinos are not facing any force after that. They travel along straight lines, free stream. But even though they are free streaming, they can undergo forward scattering without changing momentum. That's allowed. And this is what leads to all the oscillation effects, which we will talk about. And then finally, these neutrinos will arrive on Earth. We will detect them and we'll do physics with them. Okay, yes.
One question is that this electron neutrino has more interaction because there is more electron in the star matter.
Among other things, yes. Also, just the cross section is there are more channels. You can compute the cross section.
And why is the antineutrino has lesser interaction than
so, again, good question. The reason why the antineutrino cross section is a little bit smaller than the neutrino cross section has to do with the neutron to proton ratio in the star. and also the native cross section. So there is a factor of 6 or something at low energies you can compute. Okay. All right. So this is the picture I want you to have in mind, that neutrinos are trapped in the core of the star and they're escaping. Once they are able to escape, then they travel like bullets, straight lines. But even when they're traveling in a straight line, they're oscillating. And this oscillation can be affected by background matter through forward scatterings. It's not traveling in vacuum. It's traveling through a gas of electrons and other neutrinos, which are themselves oscillating. Okay, so still going to be a complicated problem, which is why there is that yellow highlighted point where I show 2 of the neutrinos crossing each other. At that point, those neutrinos will affect each other. Yes.
Only the forward scattering is important because it's the high energy.
No. So as I discussed before, non-forward scatterings only contribute to second order in the coupling constant because they can't add coherently to free propagation. So there's one per order of perturbation theory down. Yes.
Are you saying that when it's coming in a straight line, there will be oscillations?
Yes.
Why there will be oscillations?
Because neutrinos oscillate when they're traveling, and this rate of oscillation will be affected by the medium.
I see. So the Hamiltonian is basically the medium.
Is the medium effect? Yes, indeed. Yes. Yes. Yes.
Tracing of the block oscillation.
Yes, so these are block oscillations. So this is a good point for me to make connection to a bunch of things that various people here know. Neutrino oscillations are the same thing as electron spin precessions around magnetic fields, NMR, that sort of stuff. They are block oscillations. They are the same thing as what you read in chapter 1 of Sakurai. As you start with a spin along the z direction, put a magnetic field along the x direction, and the spin changes. Its direction. Sz changes as a function of time. It's all the same thing. Okay, but this neutrino oscillations in supernova is an unsolved problem, unlike the Sakurai problem that we have all known about. And you will see why. Because it's not a single particle problem. We'll see why. So one thing I want to remind you is that, yes, just the probability. If you want to compute the survival probability, we don't know how to do it. Thank you so much.
Is it the interaction parameters are known?
Everything is known. All parameters are known, all equations are known, but we don't know how to solve it. It's one of those problems totally within the standard model. It's a problem that can be given to a first-year graduate student, maybe a third-year undergrad, but it's a problem that has not been solved by anybody on the earth. It's just a very hard problem. It's just a very, irritating problem because you'll see, you have to solve 1 million partial differential equations that are coupled to each other. So see, I can give you, so consider, I give you lots of, so you know how to solve equations, linear equations. I give you a tower of linear equations, you can solve it, you just invert matrices. But if I give you a tower of nonlinear equations, can you solve it? Except numerically, of course. Numerically, you can do many things, and we will do them. But analytically, you just can't. You don't know how to solve a 5th order polynomial. All right.
So do we have this magnetic field? So do we have this magnetic field image in neutrino conversion that you try to model with? Actually, in physically, is there any correspondence?
No, so this is an analogy. It's a mathematically precise analogy that I am thinking of the quantum flavor oscillations using the same mathematics as that exists for precession of a spin around a magnetic field. Okay, there is no real magnetic field anywhere.
typically in this kind of a problem, you might try some mean field, some Hartree stuff.
Yeah.
And so on, and it doesn't.
So we will show what we can do. It works to some extent, but this is already quite mean field. What you are calling mean field, we can't solve that mean field. So there is okay, we will talk. So the point is that we are going to talk about the Wigner functions, the quasi-probability. The fluctuations around that are one order of magnitude higher difficulty problem. So this is all about the mean field. Okay, so the two things that we need to remember are there are these different neutrino flavors, and they start out by having different energy and angular spectrum. What do I mean? That because they have different cross sections, they are going to have energy spectra that are different. So the electron neutrinos, which have the most interactions, they will be emitted from the furthest out in the star, where the temperatures are lower. So their average energies are the lowest. And the non-electron neutrinos, they have the least interactions. So they are emitted from deep in the star, which is hot. And these have the highest energies. So in the green. So the energy spectra are different. More interestingly, their angular distribution is also different. Why? Consider some point inside the star. At that point, imagine that the electron neutrino has not yet decoupled. It's still fully collisional. So its angular distribution will be isotropic. That's this blue circle. But at this point, the non-electron neutrino has already decoupled, well before. Right? So I'm here, the electron neutrino is just decoupling, its angular distribution is isotropic, but the non-electron neutrino, the green one, already decoupled deeper. So at this point, the non-electron neutrino has a very forward peaked angular distribution, right? Which is this forward peak green ellipse. And these are what I mean by the momentum distributions crossing each other. So this is something that just happens normally. So the energy distributions are crossing each other, the angular distributions are crossing each other. It need not always happen. How? Imagine that the electron neutrino overall abundance is 10 times larger, then this circle will be so big and it will not cross the other one. So if the relative abundances are very skewed, you may not have a crossing of the distributions, but otherwise you can.
The momentum has nothing to do with the abundance, right? Why should it
So the
be
integral of the momentum distribution
integral
is,
of the okay.
right? So it is not the normalized distribution, it's the unnormalized
Okay.
momentum distribution. Okay?
So two overlaps are important: the energy part and the
angle part.
angle.
Yes. Two kinds of crossings.
These are experimental kind of the curves.
No, so this is just theory. This is just theory.
The top curves are all
Everything is theory.
Okay, so this blue one that you have shown, that also looks similar shape at some other point, isn't it?
You mean the circle can be circle elsewhere?
Yeah. No, whether it remains circular or
No, it will also, eventually it will also become forward peak.
yes.
Yes, yes. But at some point, let's just take some point. At that point, you have a crossing or not.
Okay.
Okay. Between any two curves, there is only one.
Yeah, I mean, if I take the whole thing,
Whole thing
I mean,
means?
three.
Yeah, yeah.
So, but I mean, is it important that, or if I say that all the curves are crossing at single point, it doesn't matter.
Anyway, very fine-tuned case. Yes, yeah. Just let's just go with the simple things first. Yeah, but yeah. So again, all of this is happening. Why? Because the different flavors have different cross sections. Okay, and this is just something that we know from the standard model. This is just measured to death. So okay, so let's start with collective instabilities. I think I have another 15 minutes.
Yes, for sure.
Okay. All right. So this is the equation that actually describes the evolution. Let me take a minute to not necessarily for you to understand this equation, but at least read this equation in the way that tells you why this problem is hard. See, usually you had a problem where time derivative of the density matrix was commutator of the Hamiltonian with the density matrix. But now you have extra terms. Both of these terms, the two terms here, both of these are because of the impact of background matter. This first term is because of electrons in the background, and this matrix L is diagonal, in the flavor basis. So this is really not that difficult. We will forget about it for now. But this is the more complicated term. And what you notice here is that when I am solving the equation for neutrino with momentum P, its motion depends on the neutrinos of all other momenta Q. So this is the commutator of the density matrix of rho with momentum Q minus the antineutrinos with the density matrix of the particular neutrino mode that I am looking at. This is what does not happen in quantum mechanics usually, right? That you don't have commutators of two density matrices so often. This is what couples the evolution of all the particles. Now let's look at how difficult this problem is. For a three flavor system, each of these density matrices is a 3×3 Hermitian matrix. For two flavors, it's 2×2. This derivative is actually not just a derivative in time, but it's the Liouville derivative. It's the v dot grad plus derivative in time. So it's a spatial gradient dot the velocity plus the time derivative. On the right hand side is an integral over all possible momenta of the neutrinos. So it's not just a partial differential equation. This is partial differential equation because of derivatives in space and time, but it's a partial integral differential equation because I have to do integrals over momenta, which are the labels of each of these rows. So it's actually a 7-dimensional problem. Now 3 spatial, 3 momentum, and 1 time. That's hard. No one has done this. No one plans to do this. So this is a good question. So we have solved it under more symmetric conditions. But the beautiful thing, or maybe the dangerous thing here, is that if you perturb around that symmetry, the solution is not always stable. So there are instabilities. So yes, we've done that. We've discovered the class of instabilities. Yes. So the key thing I want you to now take away from this thing is that the problem was hard, and there are 2 scales in the problem. One scale is the old scale, the omega, which is the delta m squared by 2ic, which is once per kilometer. And there's a second scale which is related to the neutrino density, and that's 1,000,000 times larger than this one because the neutrino density in the star is high. Okay, so 2 scales, omega and mu. Mu is 1,000,000 times omega. Once I solve this problem, yes, forget about it. That's the effect of electrons, which I'm going to ignore for now.
You are solving these equations in the region when all the 3 flavors have been coupled.
Yes, yes, they're all free streaming, but forward scattering is important. All right. So now what happens is that if something is getting hidden, I want to.
We can just make it
Oh,
minimize.
may I? Yeah, that's fine. That's good. Yeah. So I had given you this picture of what happens to Neutrino oscillations in terms of this spin precession. What background matter, high density, does is that it adds a large diagonal matrix to the Hamiltonian. Okay, which means that effectively the matrix becomes diagonal, which means that the mixing angle becomes small, effectively, which means that this B, this effective magnetic field, becomes closer and closer to the vertical axis, which means that this precession cone becomes very narrow, which means that the oscillations have very small amplitude. So this 1 minus sine squared 2 theta, this amplitude becomes really tiny. So this is the usual expectation in dense matter, that you should not have any oscillations because mixing is suppressed. However, because of this neutrino term, the last complicated term that even with a small mixing angle, you get solutions that look like this, where they're like complete 0-1 oscillations. For those who have done their classical mechanics well, they will recognize this as nutations as opposed to precessions. These are nutations of the neutrino pendulum or the neutrino gyroscope. Now the interesting thing is that these nutations have a wavelength that are not omega or frequency that's not omega, but either square root of omega times mu, correct dimensions, or just proportional to mu directly. Omega and mu are both frequencies. Mu was related to the neutrino density, omega was related to the delta m squared by 2IC. If you remember, there were those two scales. Mu was 1,000,000 times larger than omega. So that tells you that square root omega mu or mu are going to be either 1,000 or 1,000,000 times larger than omega. That's fast. Question is, when does this happen? Okay. So just another portrayal of, so instead of these oscillations, where you see the amplitude of oscillations has decreased, so it's only going all the way to 0.4. If I make the density even larger, these oscillations will be only small amplitudes. This was in 2001, before I did my PhD. During my PhD, I worked on this part, which is the slow square root omega mu style things. And in the last 5 years, we discovered this other one, where it's just linearly proportional to mu, which is 1,000,000 times larger than this one. And this, you can see again, it goes basically all the way from +4 to -4, like full order 1 oscillations. Not
and experimentally, you see these even though
there's no experiment yet.
Okay.
It's just astrophysics.
But this
no, this is not the survival probability. This is the projection. So this one is the survival probability. These are the projections of the polarization vector, which go from +1 to -1. So slightly different things, but excuse me. The last one is actually not even one polarization vector, but a sum of 4.
Larger, then you can have this kind of thing.
Yeah, when mu is large. Yeah. Okay. So let me, can I take another 10 more minutes? Okay.
Similar phenomena in NMR given your initial.
I will ask this to my NMR colleagues at the end of the talk. I've been having this chat and we'll
okay, fine.
There are certain things that have an analogy and I'll talk about them. So this fast oscillation case is now what I want to focus on in the last 10-15 minutes. I was promised 15 minutes. Okay. Sorry. I usually like to finish on time. Okay. So this fast oscillation case is hard. Okay. But we can solve it exactly in one case. Right? Instead of infinite number of momentum modes, you take just 4. And 2 of them you put neutrinos, the red ones, and 2 of them you put antineutrinos. And then you write down the equations exactly. Okay. These are this P dot is omega B cross P type equations. So this PL, PR, PL bar, PR bar are the 4 neutrino modes that I just showed. And you define some auxiliary variable, the linear combinations of them in terms of the Hamiltonian vector B. And then they have these equations of motion, where C is the cosine of the angle between the 2 beams. Okay. And then you can write down the equation for Q, which is this one, which derives out of some Lagrangian that looks like this. And then you recognize that this corresponds to Q having a potential that is a quartic. So when this angle is such that the cosine is positive, you start here and you roll down this potential. That's the instability. And when this cosine is negative, you are sitting here initially and you don't roll up the hill. Q naught is the initial value of Q. So Q is a sum of the 4 bonds, which was 4 basically to begin with, because they all start being pointing up, and then you roll down. So basically there's some way of converting this quantum mechanical problem of 4 neutrinos interacting with each other to a classical mechanics problem, which boils down to a particle rolling down a quartic potential, which you can then solve exactly, Jacobi functions. Okay. All right, so that's the one case we know how to do exactly. That was Monibrodo's thesis work with me. And then there are hundreds of other cases where you can do this numerically and you find this instability to occur. So I've already hinted or telegraphed to you, not very subtly, that this happens when there is a crossing. So there's an example of where you see this red function is where there is no crossing, it is not passing 0. And you see you don't get this. Okay? The blue function is the momentum difference of the momentum distributions. It crosses 0 here and it shows the exponential rise. Okay, so the first question that I promised that I would answer is that when do you get exponential rise? And the answer I said would be when there is a crossing of the momentum distributions. I have not proved that to you. I have given a couple of examples. Now, here is a proof that I will not go through, but if people are interested, they can stick around after the talk and I will go through the full proof. Okay, so there is some proof where you write down a bunch of equations, you use Fourier expansions and linear algebra. You basically figure out that the solutions have to depend on the solutions of some determinant equation, and then you prove that instabilities will exist only under the condition that this G function, which is the difference of the distributions, if G has both positive and negative values. So there's some proof by contradiction that you can do. Okay, so I don't want to go through the proof. This is just there for the experts. If you want, I can discuss this at the end. So now let me move on to the last part of my talk, the last 10 minutes. Okay, so there is some mathematical proof that if the difference of the momentum distributions crosses 0, you get an exponential rise. What happens afterwards? So well, numerically we've done this for many cases in simple, symmetric situations. And in the case where the crossing is in the energy spectrum, there what happens is that at the end, portions of the energy distributions of the two flavors get exchanged. So for example here, so the way to read these plots is concentrate on, let's say, this one. So you started with two flavors which look like this and this, these two energy spectra. But around this energy, the red and the black spectra have gotten exchanged. Do you see that? Is this visually clear? So you started with this tall and short spectrum, but then after the instability takes place, part of the tall one becomes short and part of the short one becomes tall. You see that the exchange is here? Okay, and this is called a spectral split. These are numerical results, no experiments yet, and this happens much more generally. So this is if there is a crossing in the energy spectrum, and this happens due to the slow instability, which is square root omega mu type. So this is old hat, old-fashioned stuff. What is the new stuff? This stuff that has to do with the angular distribution. This stuff is much more dangerous. Okay, so first of all, we had to do this problem. Note that the energy stuff is easier to do because you don't have to worry about angles. There's just one variable, energy, and you can write down a numerical, problem and you can solve it. This one is hard because you have to worry about different angles, and so you have to do at least a one space dimension, one momentum dimension. It's much harder numerical problem. So you do that numerically. Okay, so our numerics are done with one spatial dimension. We also have some results with two special dimensions. Will not talk about them here. And this is the answer, in one case at least. So this is very generic though. What here, this is the spatial dimension between the big box, which is periodic, and this is time. All the neutrinos are initially in the same flavor, pointing up, which corresponds to the blue color. As you go ahead in time, it first starts oscillating coherently everywhere, roughly. See, everywhere in space, the oscillation happens roughly at the same time. And for around first 2 or maybe 3 oscillations, you can see that there is a stripe of white and blue, reasonably coherently. But soon after, all hell breaks loose and it just, becomes very random looking. Now, this is related to the survival probability. So initially, the survival probability is oscillating coherently across space and time, and then there is some decoherence. Okay, why? So it happens in all the examples that we look at. Why?
So the decoherence happens both in space later in time, but it's kind of interesting that you have for a space, I don't know how long your coherence survives in space. Is that something that?
Very good question. Yeah. So it survives for a few oscillations.
Okay.
Because and basically the rate of decoherence and the rate of oscillation are the same. There is only one scale in this problem, and that's mu.
Okay.
So you'll see. So this is the equation. If you see, this is the equation that we are solving. Everything here is dimensionless except this mu. Okay. So there's only one scale in the problem which is dimensional. So all physics is proportional to that scale. Now, unless there is some real bizarre thing going on that there is a very small prefactor, everything will happen at the same time. Okay, and why is there decoherence? This is the answer. So because of transverse relaxation in NMR, when there are many spins which are precessing under the action of an external magnetic field, but also precessing under the action of nearby magnetic moments of the other spins. Initially, they all oscillate together coherently. But once they develop a large enough transverse component, their projection in the transverse plane scrambles. That's called transverse relaxation or spin-spin relaxation. T2 relaxation, yes, T2 relaxation. So this is something that I learned because of an assignment submitted by Krishnendu Maji in one of the courses I was teaching. I didn't know about this, and I was trying to solve this problem. And Krishnendu submitted an assignment in the StatMech course where he did simulations which showed this effect, and that sparked, the idea for me to use it in our paper. So he is thanked in the paper, and I thank him again. So T2 relaxation, indeed. So sometimes you just have to know the word, and then there's like 50 years of literature on it, and you just use it. That's what we did. So T2 relaxation happens here. Thank you, Rajdeep. And it happens when the Hamiltonian corresponding to any one of these, flavor spins becomes at a large angle with respect to the vertical. So what you see here is you see the red ones. These are the different velocities, different directions that are being emitted. So the red ones are the ones which are doing something crazy. And the reason is that their parallel, so their longitudinal part and the transverse part of the Hamiltonian are roughly the same. This is the difference of the longitudinal and transverse. This is 0. So you see for the red ones, this B field vector has become at 45 degrees. And those are the ones for which this, spin really goes to 0. Okay. So this happens in all sorts of cases. We can basically look at the average of the spins and ask what happens. These are different colors, are different initial conditions. That for each of them, you see that eventually it settles down at some value. This final settling down value, we can compute analytically. That's the answer. Okay. So just basically boils down to a 4th order equation, like a quartic equation, an algebraic equation. No? So which we can just solve. That's the answer. You can write it down explicitly in terms of initial conditions. And these dots are numerical solutions for various choices of initial conditions, and the solid lines are our solution through this equation. For 4 different classes of models, symmetries, everything, no, with infinite number of momenta in one dimension.
Quick question, if you parallel to NMR, the dephasing time is an exponential function.
It is.
So here also you get exactly one single exponent?
Yeah, like within numerical precision.
It's absolutely one t e raised to.
No. So see, you can fit it with an exponential, but there's huge fluctuation. Okay, so in the end, it's not that everything becomes depolarized. Certain neutrinos which are emitted in certain directions are depolarized more than others. So what is plotted here, focus on any one of the curves, let's say the pink one. The x-axis is the angle at which it's emitted, like the cos of the angle. So the negative ones are going backwards into the star. So at any point in the star, the neutrinos going backwards and forwards and every which way. The ones which are going backwards are completely depolarized, that's 0.5. The ones which are going forward, and this is like totally forward, they are depolarized less. When FD is 0, that means they're not depolarized. And this depolarization is predicted. These dashed lines are our theory. The solid lines are numerical simulations in every single case. There's also an understanding of why there is this depolarization in terms of diffusion of the difference of probabilities of the 2 flavors. You can derive that equation, just analytically. I don't want to do it here. Other groups have since obtained similar results. There's also
Basu, in that previous plot, is there anything to be read at 1 where all the numerical results are going up?
This value at 0?
At 1.
At 1.
Nu equal to 1.
At V equal to?
That V equal to 1.
Here.
All the numerical
this
plots
one,
are
last
going,
one.
Yeah. Is there anything?
I don't know. It's actually, I'm worried about it. I have not understood it. Yeah. So I have to admit that our solution, if you look at it, this dashed line, this is derived in a perturbation theory in V. So this dashed line is computed as a perturbation theory in the V. It doesn't work for V equal to 1, clearly, but it works, I would say, reasonably well, 10%. But I don't know what happens at V equal to 1.
Can you remind us what A is, capital A?
Yes, what V is the cosine A. It's some initial condition. Basically, it tells you about the shape of the initial momentum distributions. Thank you for that question. So the different cases are just different initial conditions, abundances. Anyway, so I told you that there's diffusion in angle space. There's also diffusion in physical space. And what's shown here is how the power in the kth Fourier mode of this fluctuation field changes with time. So initially you see it increases smoothly in a range of k's, and then once the system becomes nonlinear, there is some cascading to very large values of k's everywhere, and the system just thermalizes. Okay, this is because of mode coupling at the end, and then if you do coarse graining, basically you get smooth, everything is just smeared out because all the power is being transported to high values of k, so they're very short wavelengths, and then if you coarse grain, you don't see anything.
And what is the rough time value?
Order mu in, same as the oscillation length, few times the oscillation length. So you can see the T is 6 in orders of the oscillation length. Okay, so why do we care? Last 2 minutes. All right. K is the Fourier mode number of the field describing these fluctuations in space.
So is it, it has any feeling about plus and minus case on relation?
No. Okay, so why should we care? First, we can detect neutrinos. We have done so before. We are hoping to, in 1987, we detected about 20 neutrinos from a nearby galaxy. So we've detected supernova neutrinos. We know that these things are not just made up, but we haven't detected enough number of them to test all these theories that I told you about. Okay, so for that, there's a huge international effort. There are like so many experiments just waiting to look at the next galactic supernova. Okay, so when this happens, you're going to see tens of thousands of events at the largest detectors, and they're all going to be able to test all these theories that I just told you about. Why? Because the number of neutrinos that you see as a function of energy depends on whether these oscillations happen or not. And we can show statistically that you can rule out this flavor equilibrium idea, which is this red line, relative to the no flavor equilibrium idea, which is this green line. So this is the error bar for some experiment, and you can basically statistically you will be able to say that this supernova, the neutrinos that we saw from it, did not show fast flavor oscillation. Okay, so that's why we care. Why else do we care? Because the heating in a star depends on neutrinos. So the heating Q plus is dependent on the neutrino luminosity times the cross section divided by a 1 over r squared dilution. Everything just decreases as 1 over r squared, and then radiation at any point happens as sigma t to the power 4 in the star. So the balance between these two decides the heat transport in a star. The issue is that this sigma, the cross section, depends on the energy of the neutrino. Depends on energy as E square, and the luminosity depends on E. So the overall Q depends on the third power of energy. So E cube, roughly speaking. And now remember that the electron neutrinos interact more and the non-electron interact less. However, the non-electrons have higher energies. So if you want to deposit heat, somebody is scamming you. That they've given you these high energy non-electron neutrinos, but they have the lowest cross sections. And they've given you this high cross section electron neutrinos, but they have very little energies. So the star is not getting heated by neutrinos sufficiently. If you could somehow exchange the electron and the muon neutrinos, keeping their initial energy distributions, suddenly now you have electron neutrinos that have the energy distribution of the muon neutrino, which is higher energies on average, but they interact as electron neutrinos with the higher cross section. Right? That's nice. So you would heat the star more. Why is this important? Because for the last 100 years or so, people have been trying to understand why supernova explodes. And the idea is that neutrinos provide that heat. Simulations, however, consistently fail to explode for massive progenitors. One idea is that we have not implemented neutrino transport in this hydrodynamic simulations of stars. But the possibility is that they have not included oscillations, which would enhance the heating. So if you do that, perhaps your stars are better described by currently known physics. The fact we see supernovae explode, the fact that they don't explode on your computer could just be related to the fact that you've forgotten about oscillations. So that's a speculation. It needs to be looked at. And the last point.
But you need to invert the population that we know.
Yes. So we've done, I'm actually not showing you a few of slides which are hidden. Again, at the end, if there is time. So this is the last point and then I'll finish. Yes. So, and the final point, why should you care? Because elements are created inside stars, and the rate at which these elements are created depends on the neutron density. So this X is becoming its isotope with mass A plus 1 if it can absorb a neutron. This is our rapid neutron capture process. And you can ask what is the abundance of this heavier isotope with respect to the lighter isotope, and it depends on the log of the neutron abundance. Okay, But you see the beta equilibrium is such that the number of electron neutrinos or electron antineutrinos changes the number of neutrinos, the number of neutrons and the abundance of neutrons in the star. So if you can somehow change the number of electron neutrinos or electron antineutrinos by using oscillations, you change the neutron abundance. And that will change nucleosynthesis abundance. And that's what's shown here. So the different red and blue curves of this is Z and number of neutrons. This is our periodic table. And what's shown here is that if you put in neutrinos with some luminosity in some units, you change the abundances. Okay. Even more importantly, last one I suppose, is that if you include fast conversions, so this is the yellow one, versus no fast conversions, which is this green one, masses above 140 are enhanced. This is what corresponds to things like whatever, titanium or whatever have you. So these heavy R process elements, which have been detected in the neutron star collision that was detected by LIGO. So we are expecting to see many more such events in the next decade. So not just supernovae, but also neutron star collisions are able to test. Here I don't have the statistics to claim that it will be able to do so, because and also this theory is very preliminary, but this is a possibility. So anyway, so let's end. There's a big picture. I told you about flavor oscillations of neutrinos in stars, the fact that there is exponential rise and saturation. Eventually this flavor mixing affects the neutrino signal that you see, the nucleosynthesis in stars, and the heating of the star itself. Okay, so that's the final message. I leave you with that. Thank you for your time.
So I have a question.
Yeah, yes.
So this, I have no idea about the neutrinos.
I also.
So yeah. So what I want to ask is, why do you care about this energy distribution crossings? Because normally, if you have two objects and they are interacting, then of course you think about crossing, and so that change, that distribution, that it shows, like we talk about band inversions and so on.
Yeah.
But here, I mean, it's not really clear why you are really caring about it.
So I have a proof which I could tell you, but I don't want to do that. I don't think that's very illuminating. The quick answer is this, that you can think of when this difference of the momentum distributions crosses zero, at that point where something is changing sign, that acts like a defect, which raises energy of the system. And the system wants to undo that. And around that, in trying to undo it, it changes flavor. So imagine a bunch of spins. If everything is pointing up, maybe that's stable in some way, ferromagnetic, let's say. But if you have a system where some spins are pointing up and some are pointing down, then there is some cost, energy cost, and the system somehow wants to get rid of this energy cost. It will do whatever it can. In this case, what it does, it flips the spins in the nearby regions and creates some other distribution which is energetically more favorable. That's the explanation. And that's why you care about the difference of the energy distributions, because that's the quantity that decides the energy of the system.
So you assume that it's a completely interacting system.
Yes. Through this forward scattering only. Yes.
Okay. More questions? Zoom audience, are there questions? Okay. From the audience here. If not, I will ask a question. Basudeb, so this idea that you just invoked about the nucleosynthesis, basically. So what you're pointing out, if I can paraphrase what you're saying, that these fast oscillations are critical to sort of, or the flux of the neutrinos are critical to building up the periodic table of these elements.
Yes.
Both are critical?
Yes.
Okay.
So indeed, so what this plot shows is if there are no neutrinos, L is 0.
Right. Okay. Okay.
You'll get some value.
Okay.
Whatever.
But you can't. Okay.
When L is 5 times 10 to the 52 ergs.
Right.
Don't ask me why astrophysicists use ergs, but they do. Then you get this blue line, and then if you increase the number of neutrinos even more, you see it reduces. You see, I can even explain why it reduces. It's interesting. See, this equation, if you have more neutrinos, okay, if you have more neutrinos, let's say if I'm thinking of electron neutrinos, then the equilibrium will shift in this direction.
Okay.
So you'll reduce the number of neutrons.
Neutrons, right?
Right? If you reduce the number of neutrons, abundance of the heavier elements will decrease.
Okay.
Right?
So you can control. Okay.
And you see that.
Okay, fine. Okay.
Right?
Yeah. Okay. Okay. Any other questions? If not, let's thank Basudeb for such an exciting talk and such a difficult problem that he expanded on that even people outside the field could connect. So thank you, Basudeb, for a wonderful colloquium.
For having me.
And I will invite all of you for some snacks outside the West Canteen. Please join us. And you can have Basudeb talking about maybe the proof in a little bit more detail if you're interested. So, yeah.
Does someone want to look at the proof?
I'm giving us cheesecakes.
Okay. Okay. Thank you. Let's. Oh yes, you requested. You requested. Yes, yes. I will do that next time. Yeah.
All right. So no one wants to look at the proof.
No one wants to look at the proof.
Alok has a question.
Alok has a question. Alok. Yes. Sorry, Alok. I did not. Alok, unmute yourself.
Yeah, I don't know whether I'm keeping everybody from tea and nice snacks, but I had actually 2 short questions.
Okay, please go. Yeah, go ahead.
Basudeb, when you are actually talking about this polarization as a function of this capital A, which you said it
Initial
is
conditions.
something to do with momentum distributions. So this polarization towards the forward-going neutrinos, does that create for the energy deposition in the shock wave some kind of an advantage in certain directions and a bit of a disadvantage in other directions?
Okay, so Alok, is your question that
for a spherical supernova collapse and explosion?
So is your question that will neutrino oscillations lead to higher efficiency in certain directions and lower efficiency in other directions? Is that your question?
Roughly.
Maybe, but I haven't looked into it in detail. My guess would be it may well be the case. Yeah, I mean, that sounds reasonable because what will happen is that certain parts, so certain regions in angular distribution will convert more efficiently, as I showed you in this depolarization plot. And then your energy deposition will change in an angle dependent way.
Right. And suppose I were not considering just a spherical supernova explosion, but I'm considering double neutron star merger, which is really, it breaks the overall symmetry, the spatial symmetry.
Yes.
So will this be affecting that scenario more than the spherical collapse and explosion?
Again, great question, but I don't have an answer to this. I also don't have enough intuition for this, unfortunately. These are good questions, but I don't know the answer.
Okay. Well, thank you. I enjoyed the talk very much.
Thank you.
Thank you, Alok. Thank you for joining in.
Bye.
Thank you. I will conclude the session now. Thank you very much, Zoom audience, for joining in. And I'm hoping that you join like this every week. So thank you. Thank you very much.